continent on the opposite sides of the equator. We know, from the excellent researches of Dr. J. Host and Dr. Hector, that in New Zealand immense glaciers formerly descended to a low level, and the same plants found by Dr. Hooker on widely separated mountains in this island tell the same story of a former cold period. From facts communicated to me by the Reverend W. B. Clark, it appears also that there are traces of former glacial action on the mountains of the southeastern corner of Australia. Looking to America, in the northern half, ice-borne fragments of rock have been observed on the eastern side of the continent as far south as latitude 36 and 37 degrees, and on the shores of the Pacific, where the climate is now so different, as far south as latitude 46 degrees. Erratic boulders have also been noticed on the Rocky Mountains. In the Cordillera of South America, nearly under the equator, glaciers once extended far below their present level. In central Chile, I examined a vast mound of detritus, with great boulders crossing the Portillo Valley, which there can hardly be a doubt once formed a huge moraine. And Mr. D. Forbes informs me that he found, in various parts of the Cordillera, from latitude 13 to 30 degrees south, at about the height of 12,000 feet, deeply furrowed rocks, resembling those with which he was familiar in Norway, and likewise great masses of detritus, including grooved pebbles. Along this whole space of the Cordillera, true glaciers do not now exist even at much more considerable heights. Further south, on both sides of the continent, from latitude 41 degrees to the southernmost extremity, we have the clearest evidence of former glacial action in numerous immense boulders transported far from their parent source. From these several facts, namely, from the glacial action having extended all round the northern and southern hemispheres, from the period having been, in a geological sense, recent in both hemispheres, from its having lasted in both during a great length of time, as may be inferred from the amount of work effected, and lastly from glaciers having recently descended to a low level along the whole line of the Cordillera. It at one time appeared to me that we could not avoid the conclusion that the temperature of the whole world had been simultaneously lowered during the glacial period. But now, Mr. Kroll, in a series of admirable memoirs, has attempted to show that a glacial condition of climate is the result of various physical causes brought into operation by an increase in the eccentricity of the Earth's orbit. All these causes tend towards the same end, but the most powerful appears to be the indirect influence of the eccentricity of the orbit upon oceanic currents. According to Mr. Kroll, cold periods regularly recur every 10 or 15,000 years, and these, at long intervals, are extremely severe, owing to certain contingencies, of which the most important, as Sir C. Lyell has shown, is the relative position of the land and water. Mr. Kroll believes that the last great glacial period occurred about 240,000 years ago, and endured, with slight alterations of climate, for about 160,000 years. With respect to more ancient glacial periods, several geologists are convinced, from direct evidence, that such occurred during the Miocene and Eocene formations, not to mention still more ancient formations. But the most important result for us, arrived at by Mr. Kroll, is that whenever the northern hemisphere passes through a cold period, the temperature of the southern hemisphere is actually raised, with the winters rendered much milder, chiefly through changes in the direction of the ocean currents. So, conversely, it will be with the northern hemisphere, while the southern passes through a glacial period. This conclusion throws so much light on geographical distribution that I am strongly inclined to trust in it, but I will first give the facts which demand an explanation. In South America, Dr. Hooker has shown that besides many closely allied species, between 40 and 50 of the flowering plants of Tierra del Fuego, forming no inconsiderable part of its scanty flora, are common to North America and Europe, enormously remote as these areas in opposite hemispheres are from each other. On the lofty mountains of equatorial America, a host of peculiar species belonging to European genera occur. On the Organ Mountains of Brazil, some few temperate European, some Antarctic, and some Andean genera were found by Gardner, which do not exist in the low intervening hot countries. On the Silla of Caracas, the illustrious Humboldt long ago found species belonging to a generic characteristic of the Cordillera. In Africa, several forms characteristic of Europe, and some few representatives of the flora of the Cape of Good Hope, occur on the mountains of Abyssinia. At the Cape of Good Hope, a very few European species, believed not to have been introduced by man, and on the mountains several representative European forms are found which have not been discovered in the intertropical parts of Africa. Dr. Hooker has also lately shown that several of the plants living on the upper parts of the lofty island of Fernando Po and on the neighboring Cameroon Mountains in the Gulf of Guinea are closely related to those on the mountains of Abyssinia, and likewise to those of temperate Europe. It now also appears, as I hear from Dr. Hooker, that some of these same temperate plants have been discovered by the Reverend R.T. Lowe on the mountains of the Cape Verde Islands. This extension of the same temperate forms, almost under the equator, across the whole continent of Africa, and to the mountains of the Cape Verde archipelago, is one of the most astonishing facts ever recorded in the distribution of plants. On the Himalaya, and on the isolated mountain ranges of the peninsula of India, on the heights of Ceylon, and on the volcanic cones of Java, many plants occur, neither identically the same or representing each other, and at the same time representing plants of Europe not found in the intervening hot lowlands. A list of the genera of plants collected on the loftier peaks of Java raises a picture of a collection made on a hillock in Europe. Still more striking is the fact that peculiar Australian forms are represented by certain plants growing on the summits of the mountains of Borneo. Some of these Australian forms, as I hear from Dr. Hooker, extend along the heights of the peninsula of Malacca, and are thinly scattered on the one hand over India, and on the other hand as far north as Japan. On the southern mountains of Australia, Dr. F. Muller has discovered several European species. Other species not introduced by man occur on the lowlands, and a long list can be given, as I am informed by Dr. Hooker, of European genera found in Australia, but not in the intermediate torrid regions. In the admirable Introduction to the Flora of New Zealand by Dr. Hooker, analogous and striking facts are given in regard to the plants of that large island. Hence, we see that certain plants, growing on the more lofty mountains of the tropics in all parts of the world, and on the temperate plains of the north and south, are either the same species or varieties of the same species. It should, however, be observed that these plants are not strictly Arctic forms, for, as Mr. H.C. Watson has remarked, quote, in receding from polar toward equatorial latitudes, the alpine or mountain flora really become less and less Arctic. End quote. Besides these identical and closely allied forms, many species inhabiting the same widely sundered areas belong to genera not now found in the intermediate tropical lowlands. These brief remarks apply to plants alone, but some few analogous facts could be given in regard to terrestrial animals. In marine productions, similar cases likewise occur. As an example, I may quote a statement from the highest authority, Professor Dana, that, quote, it is certainly a wonderful fact that New Zealand should have a closer resemblance in its crustacea to Great Britain, its antipode than to any other part of the world. End quote. Sir J. Richardson also speaks of the reappearance on the shores of New Zealand, Tasmania, etc., of northern forms of fish. Dr. Hooker informs me that 25 species of algae are common to New Zealand and to Europe, but have not been found in the intermediate tropical seas. From the foregoing facts, namely the presence of temperate forms on the highlands across the whole of equatorial Africa, and along the peninsula of India, to Ceylon and the Malay archipelago, and in a less well-marked manner across a wide expanse of tropical South America, it appears almost certain that at some former period, no doubt during the most severe part of a glacial period, the lowlands of these great continents were everywhere tenanted under the equator by a considerable number of temperate forms. At this period, the equatorial climate at the level of the sea was probably about the same with that now experienced at the height of from 5,000 to 6,000 feet under the same latitude, or perhaps even rather cooler. During this, the coldest period, the lowlands under the equator must have been clothed with a mingled tropical and temperate vegetation, like that described by Hooker, as growing luxuriantly at the height of from 4,000 to 5,000 feet on the lower slopes of the Himalaya, but with, perhaps, a still greater preponderance of temperate forms. So, again, in the mountainous island of Fernando Po, in the Gulf of Guinea, Mr. Mann found temperate European forms beginning to appear at the height of about 5,000 feet. On the mountains of Panama, at the height of only 2,000 feet, Dr. Seaman found the vegetation like that of Mexico, quote, with forms of the torrid zone harmoniously blended with those of the temperate. It is a remarkable fact, strongly insisted on by Hooker in regard to America, and by Adolphe de Candolle in regard to Australia, that many more identical or slightly modified species have migrated from the north to the south than in a reversed direction. We see, however, a few southern forms on the mountains of Borneo and Abyssinia. I suspect that this preponderant migration from the north to the south is due to the greater extent of land in the north, and to the northern forms having existed in their own homes in greater numbers, and having consequently been advanced through natural selection and competition to a higher stage of perfection, or dominating power, than the southern forms. And thus, when the two sets become commingled in the equatorial regions during the alternations in the glacial periods, the northern forms were the more powerful and were able to hold their places on the mountains, and afterwards migrate southward with the southern forms. But not so the southern in regard to the northern forms. In the same manner, at the present day, we see that very many European productions cover the ground in La Plata, New Zealand, and to a lesser degree in Australia, and have beaten the natives, whereas extremely few southern forms have become naturalized in any parts of the northern hemisphere, through hides, wool, and other objects likely to carry seeds, have been largely imported into Europe during the last 2 or 3 centuries from La Plata, and during the last 40 or 50 years from Australia. The Nilgiri Mountains in India, however, offer a partial exception. For here, as I hear from Dr. Hooker, Australian forms are rapidly sowing themselves and becoming naturalized. Before the last great glacial period, no doubt the intertropical mountains were stocked with endemic alpine forms, but these have almost everywhere yielded to the more dominant forms generated in the larger areas and more efficient workshops of the north. In many islands, the native productions are nearly equaled or even outnumbered by those which have become naturalized, and this is the first stage toward their extinction. Mountains are islands on the land, and their inhabitants have yielded to those produced within the larger areas of the north, just in the same way as the inhabitants of real islands have everywhere yielded and are still yielding to continental forms naturalized through man's agency. The same principles apply to the distribution of terrestrial animals and of marine productions in the northern and southern temperate zones and on the intertropical mountains. When, during the height of the glacial period, the ocean currents were widely different to what they are now, some of the inhabitants of the temperate seas might have reached the equator. Of these, a few would perhaps at once be able to migrate southwards by keeping to the cooler currents, while others might remain and survive in the colder depths until the southern hemisphere was in its turn subjected to a glacial climate and permitted their further progress in nearly the same manner as, according to Forbes, isolated spaces inhabited by Arctic productions exist to the present day in the deeper parts of the northern temperate seas. I am far from supposing that all the difficulties in regard to the distribution and affinities of the identical and allied species, which now live so widely separated in the north and south, and sometimes on the intermediate mountain ranges, are removed on the views above given. The exact lines of migration cannot be indicated. We cannot say why certain species and not others have migrated, why certain species have been modified and have given rise to new forms, while others have remained unaltered. We cannot hope to explain such facts until we can say why one species, and not another, becomes naturalized by man's agency in a foreign land, why one species ranges twice or thrice as far, and is twice or thrice as common as another species within their own homes. Various special difficulties also remain to be solved. For instance, the occurrence, as shown by Dr. Hooker, of the same plants at points so enormously remote as Kerguelen Land, New Zealand, and Fuegia. But icebergs, as suggested by Lyell, may have been concerned in their dispersal. The existence at these and other distant points of the southern hemisphere of species which, though distinct, belong to genera exclusively confined to the south, is a more remarkable case. Some of these species are so distinct that we cannot suppose that there has been time since the commencement of the last glacial period for their migration, and subsequent modification to the necessary degree. The facts seem to indicate that distinct species, belonging to the same genera, have migrated in radiating lines from a common center, and I am inclined to look in the southern, as in the northern hemisphere, to a former and a warmer period before the commencement of the last glacial period, when the Antarctic lands, now covered with ice, supported a highly peculiar and isolated flora. It may be suspected that before this flora was exterminated during the last glacial epoch, a few forms had been already widely dispersed to various points of the southern hemisphere by occasional means of transport, and by the aid, as halting places, of now sunken islands. Thus, the southern shores of America, Australia, and New Zealand may have become slightly tinted by the same peculiar forms of life. Sir C. Lyell, in a striking passage, has speculated, in language almost identical with mine, on the effects of great alternations of climate throughout the world on geographical distribution, and we have now seen that Mr. Kroll's conclusion that successive glacial periods in the one hemisphere coincide with warmer periods in the opposite hemisphere, together with the admission of the slow modification of species, explains a multitude of facts in the distribution of the same and of the allied forms of life in all parts of the globe. The living waters have flowed during one period from the north and during another from the south, and in both cases have reached the equator, but the stream of life has flowed with greater force from the north than in the opposite direction, and has consequently more freely inundated the south. As the tide leaves its drift in horizontal lines, rising higher on the shores where the tide rises highest, so have the living waters left their living adrift on our mountain summits in a line gently rising from the Arctic lowlands to a great latitude under the equator. The various beings thus left stranded may be compared with savage races of man, driven up and surviving in the mountain fastnesses of almost every land, which serves as a record, full of interest to us, of the former inhabitants of the surrounding lowlands. End of Chapter 12, Part 2. Chapter 13 of The Origin of Species by Means of Natural Selection by Charles Darwin. This LibriVox recording is in the public domain. Recorded by Michael Armenta. Chapter 13. Geographical Distribution Continued. Distribution of freshwater productions on the inhabitants of oceanic islands, absence of batrachians and of terrestrial mammals, on the relation of the inhabitants of islands to those of the nearest mainland, on colonization from the nearest source with subsequent modification, summary of the last and present chapters. Freshwater productions. As lakes and river systems are separated from each other by barriers of land, it might have been thought that freshwater productions would not have ranged widely within the same country, and as the sea is apparently a still more formidable barrier, that they would never have extended to different countries. But the case is exactly the reverse. Not only have many freshwater species, belonging to different classes, an enormous range, but allied species prevail in a remarkable manner throughout the world. When first collecting in the fresh waters of Brazil, I will remember feeling much surprise at the similarity of the freshwater insects, shells, etc., and at the dissimilarity of the surrounding terrestrial beings compared with those of Britain. But the wide-ranging power of freshwater productions can, I think, in most cases, be explained by their having become fitted in a manner highly useful to them, for short and frequent migrations from pond to pond, or from stream to stream, within their own countries, and liability to wide dispersal would follow from this capacity as an almost necessary consequence. We can here consider only a few cases. Of these, some of the most difficult to explain are presented by fish. It was formerly believed that the same freshwater species never existed on two continents different from each other. But Dr. Gunther has lately shown that the Galaxius attenuatus inhabits Tasmania, New Zealand, the Falkland Islands, and the mainland of South America. This is a wonderful case, and probably indicates dispersal from an Antarctic center during a former warm period. This case, however, is rendered, in some degree, less surprising by the species of this genus having the power of crossing by some unknown means considerable spaces of open ocean. Thus there is one species common to New Zealand and to the Auckland Islands, though separated by a distance of about 230 miles. On the same continent, freshwater fish often range widely, and, as if capriciously, for in two adjoining river systems some of the species may be the same and some wholly different. It is probable that they are occasionally transported by what may be called accidental means. Thus, fishes still alive are not very rarely dropped at distant points by whirlwinds, and it is known that the ova retain their viability for a considerable time after removal from the water. Their dispersal may, however, be mainly attributed to changes in the level of the land within the recent period, causing rivers to flow into each other. Instances also could be given of this having occurred during floods without any change of level. The wide differences of the fish on the opposite sides of most mountain ranges, which are continuous and consequently must, from an early period, have completely prevented the inosculation of the river systems on the two sides, leads to the same conclusion. Some freshwater fish belonging to very ancient forms, and in such cases there will have been ample time for great geographical changes, and, consequently, time and means for much migration. Moreover, Dr. Gunther has recently been led, by several considerations, to infer that with fishes the same forms have a long endurance. Saltwater fish can, with care, be slowly accustomed to live in fresh water, and, according to Valenciennes, there is hardly a single group of which all the members are confined to fresh water, so that marine species belonging to a freshwater group might travel far along the shores of the sea, and could, it is probable, become adapted without much difficulty to the fresh waters of a distant land. Some species of freshwater shells have very wide ranges, and allied species, which, on our theory, are descended from a common parent, and must have proceeded from a single source, prevail throughout the world. Their distribution at first perplexed me much, as their ova are not likely to be transported by birds, and the ova, as well as the adults, are immediately killed by seawater. I could not even understand how some naturalized species have spread rapidly throughout the same country. But two facts, which I have observed, and many others, no doubt, will be discovered, throw some light on this subject. When ducks suddenly emerge from a pond covered with duckweed, I have twice seen these little plants adhering to their backs, and it has happened to me, in removing a little duckweed from one aquarium to another, that I have unintentionally stocked the one with freshwater shells from the other. But another agency is perhaps more effectual. I suspended the feet of a duck in an aquarium, where many ova of freshwater shells were hatching, and I found that members of the extremely minute and just hatched shells crawled on the feet and clung to them so firmly that when taken out of the water they could not be jarred off, though at a somewhat more advanced age they would voluntarily drop off. These just hatched mollusks, though aquatic in their nature, survived on the duck's feet in damp air from 12 to 20 hours, and in this length of time a duck or heron might fly at least 600 or 700 miles, and if blown across the sea to an oceanic island, or to any other distant point, would be sure to alight on a pool or rivulet. Sir Charles Lyell informs me that a Dicytus has been caught with an ancylus, a freshwater shell like a limbet, firmly adhering to it, and a water beetle of the same family, a columbites, once flew on board the beetle when 45 miles distant from the nearest land. How much farther it might have been blown by a favoring gale, no one can tell. With respect to plants, it has long been known what enormous ranges many freshwater and even marsh species have, both over continents and to the most remote oceanic islands. This is strikingly illustrated, according to Adolphe de Candolle, in those large groups of terrestrial plants, which have very few aquatic members, for the latter seems immediately to acquire, as if in consequence, a wide range. I think favorable means of dispersal explains this fact. I have before mentioned that earth occasionally adheres in some quality to the feet and beaks of birds. Wading birds, which frequent the muddy edges of ponds, if suddenly flushed, would be the most likely to have muddy feet. Birds of this order wander more than those of any other, and are occasionally found on the most remote and barren islands of the open ocean. They would not be likely to alight on the surface of the sea, so that any dirt on their feet would not be washed off, and when gaining the land they would be sure to fly to their natural freshwater haunts. I do not believe that botanists are aware how charged the mud of ponds is with seeds. I have tried several little experiments, but will here give only the most striking case. I took in February 3 tablespoonfuls of mud from 3 different points, beneath water, on the edge of a little pond. This mud, when dry, weighed only 6 3/4 ounces. I kept it covered up in my study for 6 months, pulling up and counting each plant as it grew. The plants were of many kinds, and were altogether 537 in number, and yet the viscid mud was all contained in a breakfast cup. Considering these facts, I think it would be an inexplicable circumstance if water birds did not transport the seeds of freshwater plants to unstocked ponds and streams situated at very distant points. The same agency may have come into play with the eggs of some of the smaller freshwater animals. Other and unknown agencies probably have also played a part. I have stated that freshwater fish eat some kinds of seeds, though they reject many other kinds after having swallowed them. Even small fish swallow seeds of moderate size, as of the yellow water lily and potamogeton. Herons and other birds, century after century, have gone on daily devouring fish. They then take flight and go to other waters or are blown across the sea, and we have seen that seeds retain their power of germination when rejected many hours afterwards in pellets or in the excrement. When I saw the great size of the seeds of that fine water lily, the nelumbium, and remembered Adolphe Candolle's remarks on the distribution of this plant, I thought that the means of its dispersal must remain inexplicable. But Audubon states that he found the seeds of the great southern water lily, probably according to Dr. Hooker, the Nelumbium luteum, in a heron's stomach. Now this bird must often have flown with its stomach thus well stocked to distant ponds, and then, getting a hearty meal of fish, analogy makes me believe that it would have rejected the seeds in the pellet in a fit state for germination. In considering these several means of distribution, it should be remembered that when a pond or stream is first formed, for instance, on a rising islet, it will be unoccupied, and a single seed or egg will have a good chance of succeeding. Although there will always be a struggle for life between the inhabitants of the same pond, however few in kind, yet as the number, even in a well-stocked pond, is small in comparison with the number of species inhabiting an equal area of land, the competition between them will probably be less severe than between terrestrial species. Consequently, an intruder from the waters of a foreign country would have a better chance of seizing on a new place than in the case of terrestrial colonists. We should also remember that many freshwater productions are low in the scale of nature, and we have reason to believe that such beings become modified more slowly than the high, and this will give time for the migration of aquatic species. We should not forget the probability of many freshwater forms having formerly ranged continuously over immense areas, and then having become extinct at intermediate points. But the wide distribution of freshwater plants and of the lower animals, whether retaining the same identical form or in some degree modified, apparently depends in main part on the wide dispersal of their seeds and eggs by animals, more especially by freshwater birds, which have the great powers of flight, and naturally travel from one piece of water to another. On the inhabitants of oceanic islands. We now come to the last of the three classes of facts which I have selected as presenting the greatest amount of difficulty with respect to distribution, on the view that not only all the individuals of the same species have migrated from some one area, but that allied species, although now inhabiting the most distant points, have proceeded from a single area, the birthplace of their early progenitors. I have already given my reasons for disbelieving in continental extensions within the period of existing species on so enormous a scale that all the many islands of the several oceans were thus stocked with their present terrestrial inhabitants. This view removes many difficulties, but it does not accord with all the facts in regard to the production of islands. In the following remarks I shall not confine myself to the mere question of dispersal, but shall consider some other cases bearing on the truth of the two theories of independent creation and of descent with modification. The species of all kinds which inhabit oceanic islands are few in number compared with those on equal continental areas. Adolphe Candolle admits this for plants and Wollaston for insects. New Zealand, for instance, with its lofty mountains and diversified stations, extending over 780 miles of latitude, together with the outlying islands of Auckland, Campbell, and Chatham, contain altogether only 960 kinds of flowering plants. If we compare this moderate number with the species which swarm over equal areas in southwestern Australia, or at the Cape of Good Hope, we must admit that some cause, independently of different physical conditions, have given rise to so great a difference in number. Even the uniform county of Cambridge has 847 plants, and the little island of Anglesey 764. But a few ferns and a few introduced plants are included in these numbers, and the comparison in some other respects is not quite fair. We have evidence that the barren island of Ascension aboriginally possessed less than half a dozen flowering plants, yet many species have now become naturalized on it, as they have in New Zealand and on every other oceanic island which can be named. In St. Helena, there is reason to believe that the naturalized plants and animals have nearly or quite exterminated many native productions. He who admits the doctrine of the creation of each separate species will have to admit that a sufficient number of the best adapted plants and animals were not created for oceanic islands, for man has unintentionally stocked them far more fully and perfectly than did nature. Although in oceanic islands the species are few in number, the proportion of endemic kinds, i.e., those found nowhere else in the world, is often extremely large. If we compare, for instance, the number of endemic land shells in Madeira, or of endemic birds in the Galapagos archipelago, with the number found on any continent, and then compare the area of the island with that of the continent, we shall see that this is true. This fact might have been theoretically expected, for, as already explained, species occasionally arriving, after long intervals of time in the new and isolated district, and having to compete with new associates, would be eminently liable to modification, and would often produce groups of modified descendants. But it by no means follows that, because in an island nearly all the species of one class are peculiar, those of another class, or of another section of the same class, are peculiar, and this difference seems to depend partly on the species which are not modified having immigrated in a body, so that their mutual relations have not been much disturbed, and partly on the frequent arrival of unmodified immigrants from the mother country, with which the insular forms have intercrossed. It should be borne in mind that the offspring of such crosses would certainly gain in vigor. I will give a few illustrations of the foregoing remarks. In the Galapagos Islands, there are 26 land birds. Of these, 21, or perhaps 23, are peculiar, whereas of the 11 marine birds, only 2 are peculiar, and it is obvious that marine birds could arrive at these islands much more easily and frequently than land birds. Bermuda, on the other hand, which lies at about the same distance from North America as the Galapagos Islands do from South America, and which has a very peculiar soil, does not possess a single endemic land bird, and we know from Mr. J. M. Jones's admirable account of Bermuda that very many North American birds occasionally, or even frequently, visit this island. Almost every year, as I am informed by Mr. E. V. Harcourt, many European and African birds are blown to Madeira. This island is inhabited by 99 kinds, of which one alone is peculiar, though very closely related to a European form, and 3 or 4 other species are confined to this island and to the Canaries, so that the islands of Bermuda and Madeira have been stocked from the neighboring continents with birds which for long ages have there struggled together and become mutually co-adapted. Hence, when settled in their new homes, each kind will have been kept by the others to its proper place and habits, and will, consequently, have been but little liable to modification. Any tendency to modification will also have been checked by intercrossing with the unmodified immigrants, often arriving from the mother country. Madeira again is inhabited by a wonderful number of peculiar land shells, whereas not one species of seashell is peculiar to its shores. Now, though we do not know how seashells are dispersed, yet we can see that their eggs, or larvae, perhaps attached to seaweed or floating timber, or to the feet of wading birds, might be transported across 300 or 400 miles of open sea far more easily than land shells. The different orders of insects inhabiting Madeira present nearly parallel cases. Oceanic islands are sometimes deficient in animals, of certain whole classes, and their places are occupied by other classes. Thus, in the Galapagos Islands, reptiles, and in New Zealand, gigantic wingless birds take, or recently took, the place of mammals. Although New Zealand is here spoken of as an oceanic island, it is in some degree doubtful whether it should be so ranked. It is of large size, and is not separated from Australia by a profoundly deep sea. From its geological character and the direction of its mountain ranges, the Reverend W. B. Clark has lately maintained that this island, as well as New Caledonia, should be considered as appurtenances of Australia. Turning to plants, Dr. Hooker has shown that in the Galapagos Islands the proportional numbers of the different orders are very different from what they are elsewhere. All such differences in number, and the absence of certain whole groups of animals and plants, are generally accounted for by supposed differences in the physical conditions of the islands. But this explanation is not a little doubtful. Facility of immigration seems to have been fully as important as the nature of the conditions. Many remarkable little facts could be given with respect to the inhabitants of oceanic islands. For instance, in certain islands not tenanted by a single mammal, some of the endemic plants have beautifully hooked seeds. Yet few relations are more manifest than that hooks serve for the transportal of seeds in the wool or fur of quadrupeds. But a hooked seed might be carried to an island by other means, and the plant then, becoming modified, would form an endemic species, still retaining its hooks, which would form a useless appendage, like the shriveled wings under the soldered wing covers of many insular beetles. Again, islands often possess trees or bushes belonging to orders which elsewhere include only herbaceous species. Now, trees, as Adelphi Cano has shown, generally have, whatever the cause may be, confined ranges. Hence, trees would be a little likely to reach distant oceanic islands, and an herbaceous plant, which had no chance of successfully competing with the many fully developed trees growing on a continent, might, when established on an island, gain an advantage over other herbaceous plants by growing taller and taller and overtopping them. In this case, natural selection would tend to add to the stature of the plant to whatever order it belonged, and thus first convert it into a bush and then into a tree. Absence of batrachians and terrestrial mammals on oceanic islands. With respect to the absence of whole orders of animals on oceanic islands, Bory St. Vincent long ago remarked that batrachians, frogs, toads, newts, are never found on any of the many islands with which the great oceans are studded. I have taken pains to verify this assertion, and have found it true, with the exception of New Zealand, New Caledonia, the Andaman Islands, and perhaps the Solomon Islands and the Seychelles. But I have already remarked that it is doubtful whether New Zealand and New Caledonia ought to be classed as oceanic islands, and this is still more doubtful with respect to the Andaman and Solomon groups and the Seychelles. This general absence of frogs, toads, and newts on so many true oceanic islands cannot be accounted for by their physical conditions. Indeed, it seems that islands are peculiarly fitted for these animals, for frogs have been introduced into Madeira, the Azores, and Mauritius, and have multiplied so as to become a nuisance. But as these animals and their spawn are immediately killed, with the exception, as far as known, of one Indian species, by sea-water, there would be great difficulty in their transportal across the sea, and therefore we can see why they do not exist on strictly oceanic islands. But why, on the theory of creation, they should not have been created there, it would be very difficult to explain. Mammals offer another and similar case. I have carefully searched the oldest voyages and have not found a single instance, free from doubt, of a terrestrial mammal excluding domesticated animals kept by the natives, inhabiting an island situated about 300 miles from a continent or great continental island. And many islands situated at a much less distance are equally barren. The Falkland Islands, which are inhabited by a wolf-like fox, comes nearest to an exception, but this group cannot be considered as oceanic, as it lies on a bank in connection with the mainland at a distance of about 280 miles. Moreover, icebergs formerly brought boulders to its western shores, and they may have formerly transported foxes, as now frequently happens in the Arctic regions. Yet it cannot be said that small islands will not support, at least, small mammals, for they occur in many parts of the world on very small islands when lying close to a continent, and hardly an island can be named on which our smaller quadrupeds have not become naturalized and greatly multiplied. It cannot be said, on the ordinary view of creation, that there has not been time for the creation of mammals. Many volcanic islands are sufficiently ancient, as shown by the stupendous degradation which they have suffered, and by their tertiary strata. There has also been time for the production of endemic species belonging to other classes, and on continents it is known that few species of mammals appear and disappear at a quicker rate than other and lower animals. Although terrestrial mammals do not occur on oceanic islands, aerial mammals do occur on almost every island. New Zealand possesses 2 bats found nowhere else in the world. Norfolk Island, the Viti Archipelago, the Bonin Islands, the Caroline and Marianne Archipelagos, and Mauritius all possess their peculiar bats. Why, it may be asked, has the supposed creative force produced bats and no other mammals on remote islands? On my view, this question can be easily answered, for no terrestrial mammal can be transported across a wide space of sea, but bats can fly across. Bats have been seen wandering by day far over the Atlantic Ocean, and 2 North American species, either regularly or occasionally, visit Bermuda at a distance of 600 miles from the mainland. I hear from Mr. Tomes, who has specially studied this family, that many species have enormous ranges and are found on continents and on far distant islands. Hence, we have only to suppose that such wandering species have been modified in their new homes in relation to their new position, and we can understand the presence of endemic bats on oceanic islands with the absence of all other terrestrial mammals. Another interesting relation exists, namely, between the depth of the sea separating islands from each other, or from the nearest continent, and the degree of affinity of their mammalian inhabitants. Mr. Windsor Earle has made some striking observations on this head, since greatly extended by Mr. Wallace's admirable researches in regard to the great Malay archipelago, which is traversed near Celebes by a space of deep ocean, and this separates 2 widely distinct mammalian faunas. On either side, the islands stand on a moderately shallow submarine bank, and these islands are inhabited by the same, or by closely allied, quadrupeds. I have not as yet had time to follow up on this subject in all quarters of the world, but as far as I have gone, the relation holds good. For instance, Britain is separated by a shallow channel from Europe, and the mammals are the same on both sides, and so it is with all the islands near the shores of Australia. The West Indian Islands, on the other hand, stand on a deeply submerged bank, nearly 1,000 fathoms in depth, and here we find American forms, but the species, and even the genera, are quite distinct. As the amount of modification which animals of all kinds undergo partly depends on the lapse of time, and as the islands, which are separated from each other, or from the mainland, by shallow channels, are more likely to have been continuously united within a recent period than the islands separated by deeper channels. We can understand how it is that a relation exists between the depth of the sea separating two mammalian faunas and the degree of their affinity, a relation which is quite inexplicable on the theory of independent acts of creation. The foregoing statements in regard to the inhabitants of oceanic islands, namely the fewness of the species, with a large proportion consisting of endemic forms, the members of certain groups, but not those of other groups in the same class, having been modified, the absence of certain whole orders, as of batrachians and of terrestrial mammals, notwithstanding the presence of aerial bats, the singular proportions of certain orders of plants, herbaceous forms having been developed into trees, etc., seem to me to accord better with the belief in the efficiency of occasional means of transport carried on during a long course of time, than with the belief in the former connection of all oceanic islands with the nearest continent. For on this latter view, it is probable that the various classes would have immigrated more uniformly, and from the species having entered in a body, their mutual relations would not have been much disturbed, and, consequently, they would either have not been modified, or all the species in a more equable manner. How many of the inhabitants of the more remote islands, whether still retaining the same specific form, or subsequently modified, have reached their present homes, but the probability of other islands having once existed as halting places, of which not a wreck now remains, must not be overlooked. I will specify one difficult case. Almost all oceanic islands, even the most isolated and smallest, are inhabited by land shells, generally by endemic species, but sometimes by species found elsewhere, striking instances of which have been given by Dr. A. Gould in relation to the Pacific. Now, it is notorious that land shells are easily killed by seawater. Their eggs, at least such as I have tried, sink in it and are killed. Yet there must be some unknown, but occasionally efficient means for their transportal. Would the just-hatched young sometimes adhere to the feet of birds roosting on the ground, and thus get transported? It occurred to me that land shells, when hibernating, and having a membranous diaphragm over the mouth of the shell, might be floated in chinks of drifted timber across moderately wide arms of the sea, and I find that several species in this state withstand uninjured an immersion in sea-water during 7 days. One shell, the Helix pomatia, after having been thus treated, and again hibernating, was put into sea-water for 20 days and perfectly recovered. During this length of time, the shell might have been carried by a marine country of average swiftness to a distance of 660 geographical miles. As this helix has a thick calcareous operculum, I removed it, and when it had formed a new membranous one, I again immersed it for 14 days in sea-water, and again it recovered and crawled away. Baron Aucapitaine has since tried similar experiments. He placed 100 land shells, belonging to 10 species, in a box pierced with holes, and immersed it for a fortnight in the sea. Out of the 100 shells, 27 recovered. The presence of an operculum seems to have been of importance, as out of 12 specimens of Cyclostoma elegans, which is thus furnished, 11 revived. It is remarkable, seeing how well the Helix pomatia resisted with me the salt water, that not one of 54 specimens belonging to 4 other species of Helix, tried by Aucapitaine, recovered. It is, however, not at all probable that land shells have often been thus transported. The feet of birds offer a more probable method. On the relations of the inhabitants of islands to those of the nearest mainland. The most striking and important fact for us is the affinity of the species which inhabit islands to those of the nearest mainland without being actually the same. Numerous instances could be given. The Galapagos archipelago, situated under the equator, lies at a distance of between 500 and 600 miles from the shores of South America. Here, almost every product of the land and of the water bears the unmistakable stamp of the American continent. There are 26 land birds. Of these, 21, or perhaps 23, are ranked as distinct species, and would commonly be assumed to have been here created. Yet the close affinity of most of these birds to American species is manifest in every character, in their habits, gestures, and tones of voice. So it is with the other animals, and with a large proportion of the plants, as shown by Dr. Hooker in his admirable Flora of this archipelago. The naturalist, looking at the inhabitants of these volcanic islands in the Pacific, distant several hundred miles from the continent, feels that he is standing on American land. Why should this be so? Why should the species which are supposed to have been created in the Galapagos archipelago and nowhere else bear so plainly the stamp of affinity to those created in America? There is nothing in the conditions of life, in the geological nature of the islands, in their height or climate, or in the proportion in which the several classes are associated together, which closely resembles the conditions of the South American coast. In fact, there is a considerable dissimilarity in all these respects. On the other hand, there is a considerable degree of resemblance in the volcanic nature of the soil, in the climate, height, and size of the islands between the Galapagos and Cape Verde archipelagos. But what an entire and absolute difference in their inhabitants! The inhabitants of the Cape Verde Islands are related to those of Africa, like those of the Galapagos to America. Facts such as these admit of no sort of explanation on the ordinary view of independent creation, whereas, on the view here maintained, it is obvious that the Galapagos Islands would be likely to receive colonists from America, whether by occasional means of transport or, though I do not believe in this doctrine, by formerly continuous land, and the Cape Verde Islands from Africa. Such colonists would be liable to modification, the principle of inheritance still betraying their original birthplace. Many analogous facts could be given. Indeed, it is an almost universal rule that the endemic productions of islands are related to those of the nearest continent, or of the nearest large island. The exceptions are few, and most of them can be explained. Thus, although Kerguelen land stands nearer to Africa than to America, the plants are related, and that very closely, as we know from Dr. Hooker's account, to those of America. But on the view that this island has been mainly stocked by seeds, brought with earth and stones on icebergs drifted by the prevailing currents, this anomaly disappears. New Zealand, in its endemic plants, is much more closely related to Australia, the nearest mainland, than to any other region, and this is what might have been expected. But it is also plainly related to South America, which, although the next nearest continent, is so enormously remote that the fact becomes an anomaly. But this difficulty partially disappears on the view that New England, South America, and the other southern lands have been stocked in part from a nearly intermediate, though distant point, namely from the Antarctic islands, when they were clothed with vegetation during a warmer tertiary period before the commencement of the last glacial period. The affinity which, though feeble, I am assured by Dr. Hooker is real, between the flora of the southwestern corner of Australia and of the Cape of Good Hope, is a far more remarkable case. But this affinity is confined to the plants, and will, no doubt, some day be explained. The same law which has determined the relationship between the inhabitants of islands and the nearest mainland is sometimes displayed on a small scale, but in a most interesting manner, within the limits of the same archipelago. Thus each separate island of the Galapagos archipelago is tenanted, and the fact is a marvelous one, by many distinct species. But these species are related to each other in a very much closer manner than to the inhabitants of the American continents, or of any other quarter of the world. This is what might have been expected, for islands situated so near to each other would almost necessarily receive immigrants from the same original source, and from each other. But how is it that many of the immigrants have been differently modified, though only in a small degree, in islands situated within sight of each other, having the same geological nature, the same height, climate, etc.? This long appeared to me a great difficulty, but it arises in chief part from the deeply seated error of considering the physical conditions of a country as the most important, whereas it cannot be disputed that the nature of the other species with which each has to compete is at least as important, and generally a far more important element of success. Now, if we look to the species which inhabit the Galapagos archipelago and are likewise found in other parts of the world, we find that they differ considerably in the several islands. This difference might indeed have been expected if the islands had been stocked by occasional means of transport, a seed, for instance, of one plant having been brought to one island, and that of another plant to another island, though all proceeding from the same general source. Hence, when in former times an immigrant first settled on one of the islands, or when it subsequently spread from one to another, it would undoubtedly be exposed to different conditions in the different islands, for it would have to compete with a different set of organisms. A plant, for instance, would find the ground best fitted for it, occupied by somewhat different species in the different islands, and would be exposed to the attacks of somewhat different enemies. If then it varied, natural selection would probably favor different varieties in the different islands. Some species, however, might spread and yet retain the same character throughout the group, just as we see some species spreading widely throughout a continent and remaining the same. The really surprising fact of this case of the Galapagos archipelago, and in a lesser degree in some analogous cases, is that each new species, after being formed in any one island, did not spread quickly to other islands. But the islands, though in sight of each other, are separated by deep arms of the sea, in most cases wider than the British Channel, and there is no reason to suppose that they have at any former period been continuously united. The really surprising fact in this case of the Galapagos archipelago, and in a lesser degree in some analogous cases, is that each new species, after being formed in any one island, did not spread quickly to the other islands, but the islands, though in sight of each other, are separated by deep arms of the sea, in most cases wider than the British Channel, and there is no reason to suppose that they have at any former period been continuously united. The currents of the sea are rapid and deep between the islands, and gales of wind are extraordinarily rare, so that the islands are far more effectually separated from each other than they appear on a map. Nevertheless, some of the species, both of those found in other parts of the world, and of those confined to the archipelago, are common to the several islands, and we may infer from the present manner of distribution that they have spread from one island to the others. But we often take, I think, an erroneous view of the probability of closely allied species invading each other's territory when put into free intercommunication. Undoubtedly, if one species has any advantage over another, it will, in a very brief time, wholly or in part, supplant it. But if both are equally well fitted for their own places, both will probably hold their separate places for almost any length of time. Being familiar with the fact that many species, naturalized through man's agency, have spread with astonishing rapidity over wide areas, we are apt to infer that most species would thus spread. But we should remember that the species which become naturalized in new countries are not generally closely allied to the aboriginal inhabitants, but are very distinct forms, belonging in a large proportion of cases, as shown by Adolphe de Candolle, to distinct genera. In the Galapagos archipelago, many, even of the birds, though so well adapted for flying from island to island, differ on the different islands. Thus there are 3 closely allied species of mocking thrush, each confined to its own island. Now, let us suppose the mocking thrush of Chatham Island to be blown to Charles Island, which has its own mocking thrush. Why should it succeed in establishing itself there? We may safely infer that Charles Island is well stocked with its own species, for annually more eggs are laid and young birds hatched than can possibly be reared. And we may infer that the mocking thrush, peculiar to Charles Island, is at least as well fitted for its home as is the species peculiar to Chatham Island. Sir C. Lyell and Mr. Wollaston have communicated to me a remarkable fact bearing on this subject, namely that Madeira and the adjoining islet of Porto Santo possess many distinct but representative species of land shells, some of which live in crevices of stone, and although large quantities of stone are annually transported from Porto Santo to Madeira, yet this latter island has not been colonized by the Porto Santo species. Nevertheless, both islands have been colonized by some European land shells, which, no doubt, had some advantage over the indigenous species. From these considerations, I think we need not greatly marvel at the endemic species which inhabit the several islands of the Galapagos archipelago, not having all spread from island to island. On the same continent, also, preoccupation has probably played an important part in checking the commingling of the species which inhabit different districts with nearly the same physical conditions. Thus, the south-east and south-west corners of Australia have nearly the same physical conditions and are united by continuous land, yet they are inhabited by a vast number of distinct mammals, birds, and plants. So it is, according to Mr. Bates, with the butterflies and other animals inhabiting the great, open, and continuous valley of the Amazons. The same principle which governs the general character of the inhabitants of oceanic islands, namely the relation to the source whence colonists could have been most easily derived, together with their subsequent modification, is of the widest application throughout nature. We see this on every mountain summit, in every lake and marsh. For alpine species, excepting in as far as the same species have become widely spread during the glacial epoch, are related to those of the surrounding lowlands. Thus, we have, in South America, alpine hummingbirds, alpine rodents, alpine plants, etc., all strictly belonging to American forms. And it is obvious that a mountain, as it became slowly upheaved, would be colonized from the surrounding lowlands. So it is with the inhabitants of lakes and marshes, excepting in so far as great facility of transport has allowed the same forms to prevail throughout large portions of the world. We see the same principle in the character of most of the blind animals inhabiting the caves of America and of Europe. Other analogous facts could be given. It will, I believe, be found universally true that wherever in 2 regions, let them be ever so distant, many closely allied or representative species occur, there will likewise be found some identical species, and wherever many closely allied species occur, there will be found many forms which some naturalists rank as distinct species, and others as mere varieties. These doubtful forms, showing us the steps in the process of modification. The relation between the power and extent of migration in certain species, either at the present or at some former period, and the existence at remote points of the world of closely allied species, is shown in another and more general way. Mr. Gould remarked to me long ago that in those genera of birds which range over the world, many of the species have wide ranges. I can hardly doubt that this rule is generally true, though difficult of proof. Among mammals, we see it strikingly displayed in bats, and in a lesser degree in the Felidae and Canidae. We see the same rule in the distribution of butterflies and beetles. So it is with most of the inhabitants of fresh water, for many of the genera in the most distinct classes range over the world, and many of the species have enormous ranges. It is not meant that all, but that some of the species have very wide ranges in the genera which range very widely. Nor is it meant that the species in such genera have, on an average, a very wide range, for this will largely depend on how far the process of modification has gone. For instance, two varieties of the same species inhabit America and Europe, and thus the species has an immense range. But if variation were to be carried a little further, the two varieties would be ranked as distinct species, and their range would be greatly reduced. Still less is it meant that species which have the capacity of crossing barriers and ranging widely, as in the case of certain powerfully winged birds, will necessarily range widely, for we should never forget that to range widely implies not only the power of crossing barriers, but the more important power of being victorious in distant lands in the struggle for life with foreign associates. But according to the view that all the species of a genus, though distributed to the most remote points of the world, are descended from a single progenitor, we ought to find, and I believe, as a general rule, we do find, that some, at least, of the species range very widely. We should bear in mind that many genera in all classes are of ancient origin, and the species in this case will have had ample time for dispersal and subsequent modification. There is also reason to believe, from geological evidence, that within each great class the lower organisms change at a slower rate than the higher. Consequently, they will have had a better chance of ranging widely, and of still retaining the same specific character. This fact, together with that of the seeds and eggs of most lowly organized forms, being very minute and better fitted for distant transportal, probably accounts for a law which has long been observed, and which has lately been discussed by Adolphe de Candolle in regard to plants, namely, that the lower of any group of organisms stands the more widely it ranges. The relations just discussed, namely, lower organisms ranging more widely than the higher, some of the species of widely ranging genera themselves ranging widely, such facts as alpine, lacustrine, and marsh productions being generally related to those which live on the surrounding lowlands and dry lands, the striking relationship between the inhabitants of islands and those of the nearest mainland, the still closer relationship of the distinct inhabitants of the islands of the same archipelago, are inexplicable on the ordinary view of the independent creation of each species, but are explicable if we admit colonization from the nearest or readiest source, together with the subsequent adaptation of the colonists to their new homes. Summary of the last and present chapters. In these chapters I have endeavored to show that if we make due allowance for our ignorance of the full effect of changes of climate and of the level of the land, which have certainly occurred within the recent period, and of other changes which have probably occurred, if we remember how ignorant we are with respect to the many curious means of occasional transport, if we bear in mind, and this is a very important consideration, how often a species may have ranged continuously over a wide area and then have become extinct in the intermediate tracts, the difficulty is not insuperable in believing that all the individuals of the same species, wherever found, are descended from common parents. And we are led to this conclusion, which has been arrived at by many naturalists, under the designation of single centers of creation, by various general considerations, more especially from the importance of barriers of all kinds, and from the analogical distribution of subgenera, genera, and families. With respect to distinct species belonging to the same genus, which on our theory have spread from one parent source, if we make the same allowances as before for our ignorance, and remember that some forms of life have changed very slowly, enormous periods of time having been thus granted for their migration, the difficulties are far from insuperable, though in this case, as in that of the individuals of the same species, they are often great. As exemplifying the effects of climatical changes on distribution, I have attempted to show how important a part the last glacial period has played, which affected even the equatorial regions, and which, during the alternations of the cold in the north and the south, allowed the productions of opposite hemispheres to mingle and left some of them stranded on the mountain summits in all parts of the world, as showing how diversified are the means of occasional transport. I have discussed at some little length the means of dispersal of freshwater productions. If the difficulties be not insuperable in admitting that in the long course of time all the individuals of the same species, and likewise of the several species belonging to the same genus, have proceeded from some one source, then all the grand leading facts of geographical distribution are explicable on the theory of migration, together with subsequent modification and the multiplication of new forms. We can thus understand the high importance of barriers, whether of land or waters, in not only separating, but in apparently forming the several zoological and botanical provinces. We can thus understand the concentration of related species within the same areas, and how it is that under different latitudes, for instance in South America, the inhabitants of the plains and mountains, of the forests, marshes, and deserts are linked together in so mysterious a manner, and are likewise linked to the extinct beings which formerly inhabited the same continent. Bearing in mind that the mutual relation of organism to organism is of the highest importance, we can see why two areas, having nearly the same physical conditions, should often be inhabited by very different forms of life. For, according to the length of time which has elapsed since the colonists entered one of the regions, or both, according to the nature of the communication which allowed certain forms and not others to enter, either in greater or lesser numbers, according or not as those which entered happened to come into more or less direct competition with each other and with the aborigines, and according as the immigrants were capable of varying more or less rapidly, there would ensue, in the two or more regions, independently of their physical conditions, infinitely diversified conditions of life. there would be an almost endless amount of organic action and reaction, and we should find some groups of beings greatly, and some only slightly modified, some developed in great force, some existing in scanty numbers, and this we do find in the several great geographical provinces of the world. On these same principles, we can understand, as I have endeavored to show, why oceanic islands should have few inhabitants, but that of these a large proportion should be endemic or peculiar, and why, in relation to the means of migration, one group of beings should all have its species of peculiar, and another group, even within the same class, should have all its species the same number with those in an adjoining quarter of the world. We can see why whole groups of organisms, as batrachians and terrestrial mammals, should be absent from oceanic islands, whilst the most isolated islands should possess their own peculiar species of aerial mammals or bats. We can see why, in islands, there should be some relation between the presence of mammals, in a more or less modified condition, and the depth of the sea between such islands and the mainland. We can clearly see why all the inhabitants of an archipelago, though specifically distinct on the several islets, should be closely related to each other, and should likewise be related, but less closely to those of the nearest continent, or other source whence immigrants might have been derived. We can see why, if there exist many closely allied or representative species in two areas, however distant from each other, some identical species will almost always there be found. As the late Edward Forbes often insisted, there is a striking parallelism in the laws of life throughout time and space, the laws governing the succession of forms in past times being nearly the same with those governing at the present time, the differences in different areas. We see this in many facts. The endurance of each species and group of species is continuous in time, for the apparent exceptions to the rule are so few that they may fairly be attributed to our not having, as yet, discovered an intermediate deposit, certain forms, which are absent in it, but which occur above and below. So, in space, it certainly is the general rule that the area inhabited by a single species, or by a group of species, is continuous, and the exceptions, which are not rare, may, as I have attempted to show, be accounted for by former migrations under different circumstances, or through occasional means of transport, or by the species having become extinct in the intermediate tracts. In both time and space, the lowly organized members of each class generally change less than the highly organized, but there are, in both cases, marked exceptions to the rule. According to our theory, these several relations throughout time and space are intelligible. For whether we look to the allied forms of life, which have changed during successive ages, or to those which have changed after having migrated into distant quarters, in both cases they are connected by the same bond of ordinary generation. In both cases, the laws of variation have been the same, and modifications have been accumulated by the same means of natural selection. End of Chapter 13. This recording is in the public domain. Chapter 14, Part 1 of The Origin of Species by Means of Natural Selection. by Charles Darwin. This LibriVox recording is in the public domain. Recorded by Michael Armenta. Chapter 14. Mutual Affinities of Organic Beings. Morphology, Embryology, Rudimentary Organs. Classification, Groups subordinate to groups, Natural System, Rules and difficulties in classification explained on the theory of descent with modification, classification of varieties, descent always used in classification, analogical or adaptive characters, affinities, general, complex, and radiating, extinction separates and defines groups, morphology, between members of the same class, between parts of the same individual, embryology, laws of, explained by variations, not supervening at an early age, and being inherited at a corresponding age, rudimentary organs, their origin explained, summary. Classification. From the most remote period in the history of the world, organic beings have been found to resemble each other in descending degrees, so that they can be classed in groups under groups. This classification is not arbitrary, like the grouping of the stars in constellations. The existence of groups would have been of simple significance if one group had been exclusively fitted to inhabit the land, and another the water, one to feed on flesh, another on vegetable matter, and so on. But the case is widely different, for it is notorious how commonly members of even the same subgroup have different habits. In the second and fourth chapters on variation and on natural selection, I have attempted to show that within each country it is the widely ranging, the much diffused and common, that is, the dominant species, belonging to the larger genera in each class, which vary most. The varieties, or incipient species, thus produced, ultimately become converted into new and distinct species, and these, on the principle of inheritance, tend to produce other new and dominant species. Consequently, the groups which are now large, and which generally include many dominant species, tend to go on increasing in size. I further attempted to show that from the varying descendants of each species trying to occupy as many and as different places as possible in the economy of nature, they constantly tend to diverge in character. This latter conclusion is supported by observing the great diversity of forms which, in any small area, come into the closest competition, and by certain facts in naturalization. I attempted also to show that there is a steady tendency in the forms which are increasing in number and diverging in character to supplant and exterminate the preceding, less divergent and less improved forms. I request the reader to turn to the diagram illustrating the action, as formerly explained, of these several principles, and he will see that the inevitable result is that the modified descendants proceeding from one progenitor become broken up into groups subordinate to groups. In the diagram, each letter on the uppermost line may represent a genus, including several species, and the whole of the genera along this upper line form together one class, for all are descended from one ancient parent, and consequently have inherited something in common. But the three genera on the left hand have, on this same principle, much in common, and form a sub-family distinct from that containing the next two genera on the right hand, which diverged from a common parent at the fifth stage of descent. These five genera have also much in common, though less than when grouped in sub-families, and they form a family distinct from that containing the three genera still further to the right hand, which diverged at an earlier period, and all these genera, descended from A, form an order instinct from the genera descended from I, so that we here have many species descended from a single progenitor grouped into genera, and the genera into subfamilies, families, and orders, all under one great class. The grand fact of the natural subordination of organic beings in groups under groups, which from its familiarity does not always sufficiently strike us, is, in my judgment, thus explained. No doubt organic beings, like all other objects, can be classed in many ways, either artificially, by single characters, or more naturally, by a number of characters. We know, for instance, that minerals and the elemental substances can be thus arranged. In this case, there is, of course, no relation to genealogical succession, and no cause can at present be assigned for their falling into groups. But with organic beings, the case is different, and the view above given accords with their natural arrangement in group under group, and no other explanation has ever been attempted. Naturalists, as we have seen, try to arrange the species, genera, and families in each class on what is called the natural system. But what is meant by this system? Some authors look at it merely as a scheme for arranging together those living objects which are most alike, and for separating those which are most unlike, or as an artificial method of enunciating, as briefly as possible, general propositions, that is, by one sentence, to give the characters common, for instance, to all mammals, by another those common to all carnivora, by another those common to the dog genus, and then, by adding a single sentence, a full description is given of each kind of dog. The ingenuity and utility of this system are indisputable, but many naturalists think that something more is meant by the natural system. They believe that it reveals the plan of the Creator, but unless it be specified whether order in time or space, or both, or what else is meant by the plan of the Creator, it seems to me that nothing is thus added to our knowledge. Expressions such as that famous one by Linnaeus, which we often meet with in a more or less concealed form, namely, that the characters do not make the genus, but that the genus gives the characters, seems to imply that some deeper bond is included in our classifications than mere resemblance. I believe that this is the case, and that community of descent, the one known cause of close similarity in organic beings, is the bond which, though observed by various degrees of modification, is partially revealed to us by our classifications. Let us now consider the rules followed in classification, and the difficulties which are encountered on the view that classification either gives some unknown plan of creation, or is simply a scheme for enunciating general propositions and of placing together the forms most like each other. It might have been thought, and was in ancient times thought, that those parts of the structure which determined the habits of life, and the general place of each being in the economy of nature, would be of very high importance in classification. Nothing could be more false. No one regards the external similarity of a mouse to a shrew, of a dugong to a whale, or of a whale to a fish, as of any importance. These resemblances, though so intimately connected with the whole life of the being, are ranked as merely, quote, adaptive or analogical characters, end quote. But to the consideration of these resemblances we shall recur. It may even be given as a general rule that the less any part of the organization is concerned with special habits, the more important it becomes for classification. As an instance, Owen, in speaking of the dugong, says, quote, the generative organs being those which are most remotely related to the habits and food of an animal, I have always regarded as affording very clear indications of its true affinities. We are, at least, likely, in the modifications of these organs, to mistake a merely adaptive for an essential character, end quote. With plants, how remarkable it is that the organs of vegetation, on which their nutrition and life depend, are of little signification, whereas the organs of reproduction, with their product, the seed and embryo, are of paramount importance. So again, in formerly discussing certain morphological characters which are not functionally important, we have seen that they are often of the highest service in classification. This depends on their constancy throughout many allied groups, and their constancy chiefly depends on any slight deviations not having been preserved and accumulated by natural selection, which acts only on serviceable characters. That the mere physiological importance of an organ does not determine its classificatory value is almost proved by the fact that, in allied groups, in which the same organ, as we have every reason to suppose, has nearly the same physiological value, its classificatory value is widely different. No naturalist can have worked at any group without being struck with this fact, and it has been fully acknowledged in the writings of almost every author. It will suffice to quote the highest authority, Robert Darwin, who, in speaking of certain organs in the Proteaceae, says their generic importance, quote, like that of all their parts, not only in this, but, as I apprehend in every natural family, is very unequal, and in some cases seems to be entirely lost, end quote. Again, in another work, he says, the genera of the Canaraceae, quote, differ in having one or more ovaria, in the existence or absence of albumin, in the imbricate or valvular aestivation. Any one of these characters singly is frequently of more than generic importance, though here, even when all taken together, they appear insufficient to separate Nestis from Canaris. End quote. To give an example among insects. In one great division of the Hymenoptera, the antennae, as Westwood has remarked, are most constant in structure. In another division they differ much, and the divisions are of quite subordinate value and classification. Yet no one will say that the antennae in these two divisions of the same order are of unequal physiological importance. Any number of instances could be given of the varying importance for classification of the same important organ within the same group of beings. Again, no one will say that rudimentary or atrophied organs are of high physiological or vital importance. Yet undoubtedly, organs in this condition are often of much value in classification. No one will dispute that the rudimentary teeth in the upper jaws of young ruminants, and certain rudimentary bones of the leg, are highly serviceable in exhibiting the close affinity between ruminants and pachyderms. Robert Darwin has strongly insisted on the fact that the position of the rudimentary florets is of the highest importance in the classification of the grasses. Numerous instances could be given of characters derived from parts which must be considered of very trifling physiological importance, but which are universally admitted as highly serviceable in the definition of whole groups. For instance, whether or not there is an open passage from the nostrils to the mouth, the only character, according to Owen, which absolutely distinguishes fish and reptiles, the inflection of the angle of the lower jaw in marsupials, the manner in which the wings of insects are folded, mere color in certain algae, mere pubescence on part of the flower in grasses, the nature of the dermal covering as hair or feathers in the vertebrata. If the ornithorhynchus had been covered with feathers instead of hair, this external and trifling character would have been considered by naturalists as an important aid in determining the degree of affinity of this strange creature to birds. The importance, for classification, of trifling characters mainly depends on their being correlated with many other characters of more or less importance. The value, indeed, of an aggregate of characters is very evident in natural history. Hence, as has often been remarked, a species may depart from its allies in several characters, both of high physiological importance and of almost universal prevalence, and yet leave us in no doubt where it should be ranked. Hence, also, it has been found that a classification founded on any single character, however important that may be, has always failed, for no part of the organization is invariably constant. The importance of an aggregate of characters, even when none are important, alone explains the aphorism enunciated by Linnaeus, namely that the characters do not give the genus, but the genus gives the character. For this seems founded on the appreciation of many trifling points of resemblance, too slight to be defined. Certain plants belonging to the Malpayaceae bear perfect and degraded flowers. In the latter, as A. D. Usseau has remarked, quote, the greater number of the characters proper to the species, to the genus, to the family, to the class, disappear, and thus laugh at our classification, end quote. When Aspicarpa produced in France during several years, only these degraded flowers, departing so wonderfully in a number of the most important points of structure from the proper type of the order, Yet M. Richard sagaciously saw, as Rousseau observes, that this genus should still be retained among the Malpiphiaceae. This case well illustrates the spirit of our classifications. Practically, when naturalists are at work, they do not trouble themselves about the physiological value of the characters which they use in defining a group or in allocating any particular species. If they find a character nearly uniform, and common to a great number of forms, and not common to others, they use it as one of high value. If common to some lesser number, they use it as of subordinate value. This principle has been broadly confessed by some naturalists to be the true one, and by none more clearly than by that excellent botanist, Auguste Saint-Hilaire. If several trifling characters are always found in combination, though no apparent bond of connection can be discovered between them, a special value is set on them. As in most groups of animals, important organs, such as those for propelling the blood or for aerating it, or those for propagating the race, are found nearly uniform. They are considered as highly serviceable in classification. But in some groups, all these, the most important vital organs, are found to offer characters of quite subordinate value. Thus, as Fritz Müller has lately remarked, in the same group of crustaceans, Cypridina is furnished with a heart, while in two closely allied genera, namely Cypris and Cytheria, there is no such organ. One species of Cypridina has well-developed bronchi, while another species is destitute of them. We can see why characters derived from the embryo should be of equal importance with those derived from the adult, for a natural classification, of course, includes all ages. But it is by no means obvious, on the ordinary view, why the structure of the embryo should be more important for this purpose than that of the adult, which alone plays its full part in the economy of nature. Yet it has been strongly urged by those great naturalists, Milne Edwards and Agassiz, that embryological characters are the most important of all, and this doctrine has very generally been admitted as true. Nevertheless, their importance has sometimes been exaggerated, owing to the adaptive characters of larvae not having been excluded. In order to show this, Fritz Müller arranged, by the aid of such characters alone, the great class of crustaceans, and the arrangement did not prove a natural one. But there can be no doubt that embryonic, excluding larval characters, are of the highest value for classification, not only with animals, but with plants. Thus the main divisions of flowering plants are founded on differences in the embryo, on the number and position of the cotyledons, and on the mode of development of the plumule and radicule. We shall immediately see why these characters possess so high a value in classification, namely, from the natural system being genealogical in its arrangement. Our classifications are often plainly influenced by chains of affinities. Nothing can be easier than to define a number of characters common to all birds, but with crustaceans any such definition has hitherto been found impossible. There are crustaceans at the opposite ends of a series which have hardly a character in common. Yet the species at both ends, from being plainly allied to others, and these to others, and so onwards, can be recognized as unequivocally belonging to this, and to no other class of the articulata. Geographical distribution has often been used, though perhaps not quite logically, in classification, more especially in very large groups of closely allied forms. Temminck insists on the utility, or even necessity of this practice in certain groups of birds, and it has been followed by several entomologists and botanists. Finally, with respect to the comparative value of the various groups of species, such as orders, suborders, families, subfamilies, and genera, they seem to be, at least at present, almost arbitrary. Several of the best botanists, such as Mr. Bentham and others, have strongly insisted on their arbitrary value. Instances could be given among plants and insects of a group first ranked by practiced naturalists as only a genus, and then raised to the rank of a subfamily or family, and this has been done. not because further research has detected important structural differences at first overlooked, but because numerous allied species with slightly different grades of difference have been subsequently discovered. All the foregoing rules and aids and difficulties in classification may be explained, if I do not greatly deceive myself, on the view that the natural system is founded on descent with modification, that the characters which naturalists consider as showing true affinity between any two or more species are those which have been inherited from a common parent, all true classification being genealogical. That community of descent is the hidden bond which naturalists have been unconsciously seeking, and not some unknown plan of creation, or the enunciation of general propositions, and the mere putting together and separating objects more or less alike. But I must explain my meaning more fully. I believe that the arrangement of the groups within each class, in due subordination and relation to each other, must be strictly genealogical in order to be natural, but that the amount of difference in the several branches or groups, though allied in the same degree in blood to their common progenitor, may differ greatly, being due to the different degrees of modification which they have undergone, and this is expressed by the forms being ranked under different genera, families, sections, or orders. The reader will best understand what is meant if he will take the trouble to refer to the diagram in the 4th chapter. We will suppose the letters A to L to represent allied genera existing during the Silurian epoch, and descended from some still earlier form. In 3 of these genera, A, F, and I, a species has transmitted modified descendants to the present day, represented by the 15 genera, A14 to Z14, on the uppermost horizontal line. Now, all these modified descendants from a single species are related in blood or descent in the same degree. They may metaphorically be called cousins to the same millionth degree, yet they differ widely and in different degrees from each other. The forms descended from A, now broken up into 2 or 3 families, constitute a distinct order from those descended from I, also broken up into 2 families. Nor can the existing species descended from A be ranked in the same genus with the parent A, or from those from I with parent I. But the existing genus, F14, may be supposed to have been but slightly modified, and it will then rank with the parent genus, F, just as some few still living organisms belong to the Silurian genera, so that the comparative value of the differences between these organic beings, which are all related to each other in the same degree in blood, has come to be widely different. Nevertheless, their genealogical arrangement remains strictly true, not only at the present time, but at each successive period of descent. All the modified descendants from A will have inherited something in common from their common parent, as will all the descendants from I. So will it be with each subordinate branch of descendants at each successive stage. If, however, we suppose any descendant of A or of I to have become so much modified as to have lost all traces of its parentage in this case, its place in the natural system will be lost, as seems to have occurred with some few existing organisms. All of the descendants of the genus F, along its whole line of descent, are supposed to have been but little modified, and they form a single genus. But this genus, though much isolated, will still occupy its proper intermediate position. The representation of the groups as here given in the diagram on a flat surface is much too simple. The branches ought to have diverged in all directions. If the names of the groups had been simply written down on a linear series, the representation would have been still less natural, and it is notoriously not possible to represent in a series, on a flat surface, the affinities which we discover in nature among the beings of the same group. Thus, the natural system is genealogical in its arrangement, like a pedigree. but the amount of modification which the different groups have undergone has to be expressed by ranking them under different so-called genera, subfamilies, families, sections, orders, and classes. It may be worthwhile to illustrate this view of classification by taking the case of languages. If we possessed a perfect pedigree of mankind, a genealogical arrangement of the races of man would afford the best classification of the various languages now spoken throughout the world. And if all extinct languages and all intermediate and slowly changing dialects were to be included, such an arrangement would be the only possible one. Yet it might be that some ancient languages had altered very little, and had given rise to few new languages, whilst others had altered much owing to the spreading, isolation, and state of civilization of the several co-descended races, and had thus given rise to many new dialects and languages. The various degrees of difference between the languages of the same stock would have to be expressed by groups subordinate to groups, but the proper, or even the most possible arrangement, would still be genealogical, and this would be strictly natural, as it would connect together all languages, extinct and recent, by the closest affinities, and would give the filiation and origin of each tongue. In confirmation of this view, let us glance at the classification of the varieties, which are known or believed to be descended from a single species. These are grouped under the species, with the subvarieties under the varieties, and in some cases, as with the domestic pigeon, with several other grades of difference. Nearly the same rules are followed as in classifying species. Authors have insisted on the necessity of arranging varieties on a natural instead of an artificial system. We are cautioned, for instance, not to class two varieties of the pineapple together, merely because their fruit, though the most important part, happens to be nearly identical. No one puts the Swedish and common turnip together, though the esculent and thickened stems are so familiar. Whatever part is found to be most constant is used in classing varieties. Thus the great agriculturist, Marshall, says the horns are very useful for this purpose with cattle, because they are less variable than the shape or color of the body, etc., whereas with sheep the horns are much less serviceable, because less constant. In classing varieties, I apprehend that if we had a real pedigree, a genealogical classification would be universally preferred, and it has been attempted in some cases, for we might feel sure, whether there had been more or less modification, that the principle of inheritance would keep the forms together which were allied in the greatest number of points. In tumbler pigeons, though some of the sub-varieties differ in the most important character of the length of the beak, yet all are kept together from having the common habit of tumbling. But the short-faced breed has nearly or quite lost this habit. Nevertheless, without any thought on the subject, these tumblers are kept in the same group, because allied in blood and alike in some other respects. With species in a state of nature, every naturalist has, in fact, brought descent into his classification, for he includes, in his lowest grade, that of species, the two sexes, and how enormously these sometimes differ in the most important characters is known to every naturalist. Scarcely a single fact can be predicated in common of the adult males and hermaphrodites of certain cirripedes, and yet no one dreams of separating them. As soon as the three orchidean forms, Monacanthus, Myanthus, and Catasetum, which had previously been ranked as three distinct genera, were known to be sometimes produced on the same plant, they were immediately considered as varieties. And now I have been able to show that they are the male, female, and hermaphrodite forms of the same species. The naturalist includes, as one species, the various larval stages of the same individual, however much they may differ from each other, and from the adult, as well as the so-called alternate generations of Steenstrup, which can only, in a technical sense, be considered as the same individual. He includes monsters and varieties, not from their partial resemblance to the parent form, but because they are descended from it. As descent has universally been used as classing together the individuals of the same species, though the males and females and larvae are sometimes extremely different, and as it has been used in classing varieties which have undergone a certain, and sometimes a considerable amount of modification, may not this same element of descent have been unconsciously used in grouping species under genera, and genera under higher groups, all under the so-called natural system? I believe it has been unconsciously used, and thus only can I understand the several rules and guides which have been followed by our best systematists. As we have no written pedigrees, we are forced to trace community of descent by resemblances of any kind. Therefore, we choose those characters which are the least likely to have been modified in relation to the conditions of life to which each species has been recently exposed. Rudimentary structures on this view are as good as, or even sometimes better than, other parts of the organization. We care not how trifling a character may be, let it be the mere inflection of the angle of the jaw, the manner in which an insect's wing is folded, whether the skin be covered by hair or feathers. If it prevail throughout many and different species, especially those having very different habits of life, it assumes high value, for we can account for its presence in so many forms with such different habits only by inheritance from a common parent. We may err in this respect in regard to single points of structure, but when several characters, let them be ever so trifling, concur throughout a large group of beings having different habits, we may feel almost sure, on the theory of descent, that these characters have been inherited from a common ancestor, and we know that such aggregated characters have a special value in classification. We can understand why a species, or a group of species, may depart from its allies in several of its most important characteristics, and yet be safely classed with them. This may be safely done, and it is often done, as long as a sufficient number of characters, let them be ever so unimportant, betrays the hidden bond of community of descent. Let two forms have not a single character in common, yet if these extreme forms are connected together by a chain of intermediate groups, we may at once infer their community of descent, and we put them all into the same class. As we find organs of high physiological importance, those which serve to preserve life under the most diverse conditions of existence, are generally the most constant, we attach a special value to them. But if these same organs, in another group or section of group, are found to differ much, we at once value them less in our classification. We shall presently see why embryological characters are of such high classificatory importance. Geographical distribution may sometimes be brought usefully into play in classing large genera, because all the species of the same genus, inhabiting any distinct and isolated region, are in all probability descended from the same parents. Analogical resemblances. We can understand, on the above views, the very important distinction between real affinities and analogical or adaptive resemblances. Lamarck first called attention to this subject, and he has been ably followed by Maclay and others. The resemblance in the shape of the body and in the fin-like anterior limbs between dugongs and whales, and between these two orders of mammals and fishes, are analogical. So is the resemblance between a mouse and a shrew mouse, Sorex, which belong to different orders, and the still closer resemblance, insisted on by Mr. Mivart, between the mouse and a small marsupial animal, Antechinus, of Australia. These latter resemblances may be accounted for, as it seems to me, by adaptation for similarly active movements through thickets and herbage, together with concealment from enemies. Among insects there are innumerable instances. Thus Linnaeus, misled by external appearances, actually classed an homopterous insect as a moth. We see something of the same kind even with our domestic varieties, as in the strikingly similar shape of the body in the improved breeds of the Chinese and common pig, which are descended from distinct species, and in the similarly thickened stems of the common and specifically distinct Swedish turnip. The resemblance between the greyhound and race-horse is hardly more fanciful than the analogies which have been drawn by some authors between widely different animals. On the view of characters being of real importance for classification, only in so far as they reveal descent, we can clearly understand why analogical or adaptive characters, although of the utmost importance to the welfare of the being, are almost valueless to the systematist. For animals, belonging to two most distinct lines of descent, may have become adapted to similar conditions, and thus have assumed a close external resemblance, but such resemblances will not reveal, will rather tend to conceal their blood relationship. We can thus also understand the apparent paradox that the very same characters are analogical when one group is compared with another, but give true affinities when the members of the same group are compared together. Thus, the shape of the body and fin-like limbs are only analogical when whales are compared with fishes, being adaptations in both classes for swimming through the water. But between the several members of the whale family, the shape of the body and the fin-like limbs offer characters exhibiting true affinity, for as these parts are so nearly similar throughout the whole family, we cannot doubt that they have been inherited from a common ancestor. So it is with fishes. Numerous cases could be given of striking resemblances in quite distinct beings between single parts or organs which have been adapted for the same functions. A good instance is afforded by the close resemblance of the jaws of the dog and Tasmanian wolf, or Thylacinus, animals which are widely sundered in the natural system. But this resemblance is confined to general appearance, as in the prominence of the canines and in the cutting shape of the molar teeth. For the teeth really differ much. Thus the dog has on each side of the upper jaw 4 premolars and only 2 molars, while the Thylacinus has 3 premolars and 4 molars. The molars also differ much in the two animals in relative size and structure. The adult dentition is preceded by a widely different milk dentition. Anyone may, of course, deny that the teeth in either case have been adapted for tearing flesh through the natural selection of successive variations. But if this be admitted in the one case, it is unintelligible to me that it should be denied in the other. I'm glad to find that so high an authority as Professor Flower has come to this same conclusion. The extraordinary cases given in a former chapter of widely different fishes possessing electric organs, of widely different insects possessing luminous organs, and of orchids and asclepiads having pollen masses with viscid discs come under this same head of analogical resemblances. But these cases are so wonderful that they were introduced as difficulties or objections to our theory. In all such cases, some fundamental difference in the growth or development of the parts, and generally in their matured structure, can be detected. The end gained is the same, but the means, though appearing superficially to be the same, are essentially different. The principle formerly alluded to under the term of analogical variation has probably, in these cases, often come into play. That is, the members of the same class, although only distantly allied, have inherited so much in common in their constitution that they are apt to vary under similar exciting causes in a similar manner, and this would obviously aid in the acquirement, through natural selection, of parts or organs strikingly like each other, independently of their direct inheritance from a common progenitor. As species belonging to distinct classes have often been adapted by successive slight modifications to live under nearly similar circumstances, to inhabit, for instance, the 3 elements of land, air, and water, we can perhaps understand how it is that a numerical parallelism has sometimes been observed between the subgroups of distinct classes. A naturalist, struck with a parallelism of this nature, by arbitrarily raising or sinking the value of the groups in several classes, and all our experience shows that their valuation is as yet arbitrary, could easily extend the parallelism over a wide range, and thus the septenary, quinary, quaternary, and ternary classifications have probably arisen. There is another and curious class of cases in which close external resemblance does not depend on adaptation to similar habits of life, but has been gained for the sake of protection. I allude to the wonderful manner in which certain butterflies imitate, as first described by Mr. Bates, other and quite distinct species. This excellent observer has shown that in some districts of South America, where, for instance, an ithomia abounds in gaudy swarms, another butterfly, namely a leptalis, is often found mingled in the same flock, and the latter so closely resembles the ithomia in every shade and stripe of color, and even in the shape of its wings, that Mr. Bates, with his eyes sharpened by collecting during 11 years, was, though always on his guard, continually deceived. When the mockers and the mocked are cut and compared, they are found to be very different in essential structure, and to belong not only to distinct genera, but often to distinct families. Had this mimicry occurred in only one or two instances, it might have been passed over as a strange coincidence. But if we proceed from a district where one leptalis imitates an ithomia, another mocking and mocked species belonging to the same two genera, equally close in their resemblance, may be found. Altogether no less than 10 genera are enumerated, which include species that imitate other butterflies. The mockers and mocked always inhabit the same region. We never find an imitator living remote from the form which it imitates. The mockers are almost invariably rare insects. The mocked, in almost every case, abounds in swarms. In the same district in which a species of leptalis closely imitates an ithomia, there are sometimes other Lepidoptera mimicking the same ithomia, so that, in the same place, species of 3 genera of butterflies, and even a moth, are found all closely resembling a butterfly belonging to a 4th genus. It deserves especial notice that many of the mimicking forms of the leptalis, as well as of the mimicked forms, can be shown by a graduated series to be merely varieties of the same species, while others are undoubtedly distinct species. But why, it may be asked, are certain forms treated as the mimicked and others as the mimickers? Mr. Bates satisfactorily answers this question by showing that the form which is imitated keeps the usual dress of the group to which it belongs, while the counterfeiters have changed their dress and do not resemble their nearest allies. We are next led to inquire what reason can be assigned for certain butterflies and moths so often assuming the dress of another and quite distinct form. Why, to the perplexity of naturalists, has nature condescended to the tricks of the stage? Mr. Bates has, no doubt, hit on the true explanation. The mocked forms, which always abound in numbers, must habitually escape destruction to a large extent, otherwise they could not exist in such swarms, and a large amount of evidence has now been collected, showing that they are distasteful to birds and other insect-devouring animals. The mocking forms, on the other hand, that inhabit the same district, are comparatively rare, and belong to rare groups. Hence they must suffer habitually from some danger, for otherwise, from the number of eggs laid by all butterflies, they would, in 3 or 4 generations, swarm over the whole country. Now, if a member of one of these persecuted and rare groups were to assume a dress so like that of a well-protected species that it continually deceived the practiced eyes of an entomologist, it would often deceive predaceous birds and insects, and thus often escape destruction. Mr. Bates may almost be said to have actually witnessed the process by which the mimickers have come so closely to resemble the mimicked, for he found that some of the forms of the leptalis, which mimic so many other butterflies, varied in an extreme degree. In one district several varieties occurred, and of these one alone resembled, to a certain extent, the common ithomia of the same district. In another district there were 2 or 3 varieties, one of which was much commoner than the others, and this closely mocked another form of ithomia. From facts of this nature, Mr. Bates concludes that the leptalist first varies, and when a variety happens to resemble in some degree any common butterfly inhabiting the same district, this variety, from its resemblance to a flourishing and little persecuted kind, has a better chance of escaping destruction from predaceous birds and insects, and is consequently oftener preserved. Quote, the less perfect degrees of resemblance being generation after generation eliminated, and only the others left to propagate their kind. End quote. So that here we have an excellent illustration of natural selection. Messrs. Wallace and Triman have likewise described several equally striking cases of imitation in the Lepidoptera of the Malay archipelago and Africa, and with some other insects. Mr. Wallace has also detected one such case with birds, but we have none with the larger quadrupeds. A much greater frequency of imitation with insects than with other animals is probably the consequence of their small size. Insects cannot defend themselves, except, indeed, the kinds furnished with a sting, and I've never heard of an instance of such kinds mocking other insects, though they are mocked. Insects cannot easily escape by flight from the larger animals which prey on them. Therefore, speaking metaphorically, they are reduced, like most weak creatures, to trickery and dissimulation. It should be observed that the process of imitation probably never commenced between forms widely dissimilar in color, but starting with species already somewhat like each other, the closest resemblance, if beneficial, could readily be gained by the above means, and if the imitated form was subsequently and gradually modified through any agency, the imitating form would be led along the same track, and thus be altered to almost any extent, so that it might ultimately assume an appearance or coloring wholly unlike that of the other members of the family to which it belonged. There is, however, some difficulty on this head, for it is necessary to suppose, in some cases, that ancient members belonging to several distinct groups, before they had diverged to their present extent, accidentally resembled a member of another and protected group in a sufficient degree to afford some slight protection, this having given the basis for the subsequent acquisition of the most perfect resemblance. On the nature of the affinities connecting organic beings. As the modified descendants of dominant species belonging to the larger genera tend to inherit the advantages which made the groups to which they belong large and their parents dominant, they are almost sure to spread widely and to seize on more and more places in the economy of nature. The larger and more dominant groups within each class thus tend to go on increasing in size, and they consequently supplant many smaller and feebler groups. Thus we can account for the fact that all organisms, recent and extinct, are included under a few great orders, and under still fewer classes. As showing how few the higher groups are in number, and how widely they are spread throughout the world, the fact is striking that the discovery of Australia has not added an insect belonging to a new class, and that in the vegetable kingdom, as showing how few the higher groups are in number, and how widely they are spread throughout the world, the fact is striking that the discovery of Australia has not added an insect belonging to a new class, and that, in the vegetable kingdom, as I learned from Dr. Hooker, it has added only 2 or 3 families of small size. In the chapter on geological succession, I attempted to show, on the principle of each group having generally diverged much in character during the long-continued process of modification, how it is that the more ancient forms of life often present characters, in some degree, intermediate between existing groups, as some few of the old and intermediate forms having transmitted to the present day descendants but little modified, these constitute our so-called osculent or aberrant groups. The more aberrant any form is, the greater must be the number of connecting forms which have been exterminated and utterly lost. And we have evidence of aberrant groups having suffered severely from extinction, for they are almost always represented by extremely few species, and such species as do occur are generally very distinct from each other, which again implies extinction. The genera Ornithorhynchus and Lepidosiren, for example, would not have been less aberrant had each been represented by a dozen species instead of, as at present, by a single one, or by two or three. We can, I think, account for this fact only by looking at aberrant groups as forms which have been conquered by more successive competitors, with a few members still preserved under unusually favorable conditions. Mr. Waterhouse has remarked that when a member belonging to one group of animals exhibits an affinity to a quite distinct group, this affinity in most cases is general and not special. Thus, according to Mr. Waterhouse, of all rodents, the bizcacha is most nearly related to marsupials, but in the points in which it approaches this order, its relations are general. That is, not to any one marsupial species more than to another. As these points of affinity are believed to be real and not merely adaptive, they must be due, in accordance with our view, to inheritance from a common progenitor. Therefore, we must suppose either that all rodents, including the bizcacha, branched off from some ancient marsupial, which will naturally have been more or less intermediate in character with respect to all existing marsupials, or that both rodents and marsupials branched off from a common progenitor, and that both groups have since undergone much modification in divergent directions. On either view, we must suppose that the bizcacha has retained, by inheritance, more of the character of its ancient progenitor than have other rodents, and therefore it will not be specially related to any one existing marsupial, but indirectly to all, or nearly all, marsupials, from having partially retained the character of their common progenitor, or of some early member of the group. On the other hand, of all marsupials, as Mr. Waterhouse has remarked, the Phascolomys resembles, most nearly, not any one species, but the general order of rodents. In this case, however, it may be strongly suspected that the resemblance is only analogical, owing to the Phascolomys having become adapted to habits like those of a rodent. The elder de Candolle has made nearly similar observations on the general nature of the affinities of distinct families of plants, on the principle of the multiplication and gradual divergence in character of the species descended from a common progenitor, together with their retention, by inheritance, of some characters in common, we can understand the excessively complex and radiating affinities by which all the members of the same family, or higher group, are connected together. For the common progenitor of a whole family, now broken up by extinction into distinct groups and subgroups, will have transmitted some of its characters, modified in various ways and degrees, to all the species, and they will consequently be related to each other by circuitous lines of affinity of various lengths, as may be seen in the diagram so often referred to, mounting up through many predecessors. As it is difficult to show the blood relationship between the numerous kindred of any ancient and noble family, even by the aid of a genealogical tree, and almost impossible to do so without this aid, we can understand the extraordinary difficulty which naturalists have experienced in describing, without the aid of a diagram, the various affinities which they perceive between the many living and extinct members of the same great natural class. Extinction, as we have seen in the 4th chapter, has played an important part in defining and widening the intervals between the several groups in each class. We may thus account for the distinctness of whole classes from each other, for instance, of birds from all other vertebrate animals, by the belief that many ancient forms of life have been utterly lost, through which the early progenitors of birds were formerly connected with the early progenitors of the other, and at that time less differentiated vertebrate classes. There has been much less extinction of the forms of life which once connected fishes with batrachians. There has been still less within some whole classes, for instance, the crustacea, for here the most wonderfully diverse forms are still linked together by a long and only partially broken chain of affinities. Extinction has only defined the groups, it has by no means made them. For if every form which has ever lived on earth were suddenly to reappear, though it would be quite impossible to give definitions by which each group could be distinguished, still a natural classification, or at least a natural arrangement, would be possible. We shall see this by turning to the diagram. The letters A to L may represent 11 Silurian genera, some of which have produced large groups of modified descendants, with every link in a branch and sub-branch still alive, and the links not greater than those between existing varieties. In this case, it would be quite impossible to give definitions by which the several members of the several groups could be distinguished from their more immediate parents and descendants, yet the arrangement in the diagram would still hold good and would be natural, for, on the principle of inheritance, all the forms descended, for instance from A, would have something in common. In a tree we can distinguish this or that branch, though at the actual fork the two unite and blend together. We could not, as I've said, define the several groups, but we could pick out types or forms representing most of the characters of each group, whether large or small, and thus give a general idea of the value of the differences between them. This is what we should be driven to, if we were ever to succeed in collecting all the forms in any one class which have lived throughout all time and space. Assuredly, we shall never succeed in making so perfect a collection. Nevertheless, in certain classes, we are tending toward this end, and Milne Edwards has lately insisted, in an able paper, on the high importance of looking to types, whether or not we can separate and define the groups to which types belong. Finally, we have seen that natural selection, which follows from the struggle for existence, and which almost inevitably leads to extinction, and divergence of character in the descendants from any one parent species, explains that great and universal feature in the affinities of all organic beings, namely their subordination in group unto group. We use the element of descent in classing the individuals of both sexes and of all ages under one species, although they may have but few characters in common. We use descent in classing acknowledged varieties, however different they may be from their parents, and I believe that this element of descent is the hidden bond of connection which naturalists have sought under the term of the natural system. On this idea of the natural system being, in so far as it has been perfected, genealogical in its arrangement, with the grades of difference expressed by the terms genera, families, orders, etc., we can understand why we value certain resemblances far more than others, why we use rudimentary and useless organs, or others of trifling physiological importance, why, in finding the relations between one group and another, we summarily reject analogical or adaptive characters, and yet use these same characters within the limits of the same group. We can clearly see how it is that all living and extinct forms can be grouped together within a few great classes, and how the several members of each class are connected together by the most complex and radiating lines of affinities. We shall never, probably, disentangle the inextricable web of the affinities between the members of any one class, but when we have a distinct object in view, and do not look to some unknown plan of creation, we may hope to make sure but slow progress. Professor Haeckel, in his Générale Morphologie, and in other works, has recently brought his great knowledge and abilities to bear on what he calls phylogeny, or the lines of descent of all organic beings. In drawing up the several series, he trusts chiefly to embryological characters, but receives aid from homologous and rudimentary organs, as well as from the successive periods at which the various forms of life are believed to have first appeared in our geological formations. He has thus boldly made a great beginning, and shows us how classification will, in the future, be treated. End of Chapter 14, Part 1. Chapter 14, Part 2, of The Origin of Species by Means of Natural Selection, by Charles Darwin. This LibriVox recording is in the public domain. Recorded by Michael Armenta. Morphology. We have seen that the members of the same class, independently of their habits of life, resemble each other in the general plan of their organization. This resemblance is often expressed by the term, quote, unity of type, end quote, or by saying that the several parts and organs in the different species of the class are homologous. The whole subject is included under the general term of morphology. This is one of the most interesting departments of natural history, and may almost be said to be its very soul. What can be more curious, then, that the hand of a man, formed for grasping, that of a mole for digging, the leg of the horse, the paddle of the porpoise, and the wing of the bat, should all be constructed on the same pattern, and should include similar bones in the same relative positions? How curious it is to give a subordinate, though striking instance, that the hind feet of the kangaroo, which are so well fitted for bounding over the open plains, those of the climbing leaf-eating koala, equally well fitted for grasping the branches of trees, those of the ground-dwelling insect or root-eating bandicoots, and those of some other Australian marsupials, should all be constructed on the same extraordinary type, namely with the bones of the second and third digits extremely slender and enveloped within the same skin, so that they appear like a single toe furnished with 2 claws. Notwithstanding this similarity of pattern, it is obvious that the hind feet of these several animals are used for as widely different purposes as it is possible to conceive. Their case is rendered all the more striking by the American opossums, which follow nearly the same habits of life as some of their Australian relatives, having feet constructed on the ordinary plan. Professor Flower, from whom these statements are taken, remarks in conclusion, quote, "We may